Sì, lo so.
Come vuoi tu, cioè, tu mi dai il tempo di partenza e mi dai anche il tempo di arresto in realtà. Ma
maybe we should open our morning section. Okay, so it is a pleasure to introduce Professor Alberto Setti from University of Insubria. He will give us a talk on global maximum principles on complete manifolds with boundary. Thank you.
Bom dia. This is about all the Portuguese I can negotiate. So first of all, it's a pleasure to thank the organizers and in particular the Tang for the invitation and the opportunity to give a talk here. I'm going to report on joint work with Stefano Pigola and Deborah Impera. And the goal is to apply maximum principles and obtain suitable formula maximum principles and obtain height estimates and slice estimates for graphs in this talk in a product. And I'd like to start with the compact case. So you take a graph, and it's known by a graph over an open set in R2. It's known by work by Serin and Heinz that if the graph has constant mean curvature, then it satisfies a height estimate. And the proof is actually a fairly straightforward. Right. We're going to see a generalization of this result to the case of domains in a complete Riemannian manifold. With suitable assumptions on the curvature of the ambient space. So you have a graph, you have the boundary of the graph that lies on the slice at height 0, say, and even in this context, the graph satisfies the height estimate that we were mentioning before. Here is a sketch of the proof. First thing you do is you pull back the metric from the graph to the domain on the base manifold and denote by a sigma the objects. Then it's well known that the height function satisfies this differential equation. The assumptions on the curvature imply that U is in fact superharmonic with respect to the Laplacian and satisfies zero boundary conditions on the boundary. And the maximum principle says that it attains a minimum on the boundary, and so U is bigger than or equal to 0 on the domain. Then you take this other function, and it is known by work of Alias and Dacher that under the assumption that the Ricci curvature is bigger than or equal to 0, the function W is subharmonic. It is non-positive on the boundary, and again, by the maximum principle, it is everywhere non-positive, and this gives the other inequality in the result. With similar arguments, one can obtain this version of a slice theorem. Again, you have a compact domain in a Riemannian manifold. Now we don't need any curvature assumption on the base manifold, boundary dm, and outward unit normal ni. You have a graph over the domain M, and you assume that this time the mean curvature is non-positive with respect to the downward pointing Gauss map. And then if either one of these two assumptions, this says that on the boundary the graph lies on the slice, and it is globally, the graphing function is positive, or else the Gauss map makes a suitable angle with the interior pointing normal to the domain M at the boundary, so it's actually pointing minus ni is the interior pointing. And the conclusion is that in this case, sigma is a slice, is contained in a slice, which of course will be the slice M cross 0 in case I. And this is actually even easier in terms of proof. You consider the usual equation for the curvature of a graph, mean curvature of a graph. It follows that the divergence of this vector field is non-positive, and so applying the usual maximum principle, the supremum of u on M is the supremum of u on the boundary. So if you have Dirichlet boundary conditions, you conclude that u is less than or equal to 0. And since we assumed to begin with that u was bigger than or equal to 0, u is identically 0. And in the other case, the conclusion follows from an application of the boundary point lemma. So we're going to recover these two results in the case of manifolds with boundary not necessarily compact. And the idea is that already in the case of manifolds without boundary, it's pretty well established that a useful substitute of compactness tends to be parabolicity. And in the case of manifold with boundary, there are actually at least two fruitful definitions of parabolicity. We're going to adopt let's say, the most canonical one as described, say, for instance, in the seminal work by Grigorian. So, we will go back to other possible definitions of parabolicity towards the end of the talk. So, as I was saying, there have been extensions to unbounded domains. For instance, a paper by Ross and Rosenberger, which extended the result in this situation. The proof uses in a somewhat substantial way the homogeneity of Rn, R2 in this case, and so it is not immediately extendable to the case of general manifolds. And we will try to recover the result using parabolicity instead. So, as I was saying, we're going to use the Grigorian definition of parabolicity in the case of manifold with boundary. This definition essentially assumes Neumann boundary conditions on the boundary. So you have a manifold with a smooth boundary, and when you take a domain in the manifold, you divide the topological boundary of the domain D in the genuine boundary and the boundary that the domain shares with the boundary of M. And we will see that what really matters is the behavior of functions on the D0 part of the boundary. And so this is the definition, we say, of Neumann subsolution of the Laplace equation. We are actually simply giving a weak interpretation of this kind of differential inequality. For C2 functions, a Neumann subsolution is a function that satisfies Laplacian of u greater than or equal to 0 with this kind of boundary condition. And again, since we're going to work with W12 local functions, we use this kind of weak formulation. Notice that there is no, this phi is compactly supported in D, which actually means that it's supposed to vanish near the boundary D0 of D, but there is no condition on the boundary D1 on D, and this encodes the condition du over dni less than or equal to 0. And one, of course, can define super solution and solutions in exactly the same manner. And this is the definition. A boundary, a manifold with boundary is parabolic if bounded above weak Neumann subsolution of Laplace equation are constant. From the point of view of the relevant inequality, this is it. In classical terms, du greater than or equal to 0, du over dni less than or equal to 0, and u bounded above implies u necessarily constant. So, so this is the definition, and in the case of manifold without boundary, there are a lot of characterizations of parabolicity in terms of capacity, appropriate. Actually, typically, parabolicity is defined in terms of capacity, but validity of appropriate versions of the divergence theorem. This is the so-called Kelvin-Nevalina-Royden criterion. Comparison results, and it is also known that volume growth conditions imply parabolicity. And we're going briefly to see that this is also the case for manifolds with boundary. We will start actually with the so-called Alfors maximum principle. And no, sorry, we actually start with the volume growth conditions. In order to prove, one of the possible proofs that a manifold is parabolic, provided its volume growth is controlled, typically it is at most quadratic, goes through, is done by showing that, by building, using the volume of the area, actually, of the boundary of balls as a barrier for the differential equation satisfied by the subharmonic function, which is supposed to be 0. And the proof is essentially based on the validity of the coarea formula. And so since the coarea formula actually still holds, provided we apply it in a proper way, we recover the result. Here's the notation. BMR is the ball with its boundary. This is the distance from a fixed point. It is still true that it is Lipschitz, and therefore almost everywhere differentiable in the interior of M. Oh yes, I didn't actually say. This is M minus its boundary, so the points which have neighborhoods diffeomorphic to balls in Rn. You have Gauss lemma, the coarea for, what happened? Sorry. The coarea formula still holds, and this allows us to obtain this result. So the idea is that these two conditions roughly correspond to an at most quadratic growth of the volumes. And so it should be pointed out that so the weakest condition is this one. But this is essentially more stable. So, for instance, this condition is even stable by rough isometries. And so this is important in order to obtain parabolicity. So once we have this, we move to the maximum principle, Alford's maximum principle. And essentially, again, this is an extension of what happens in the case of domain with boundary, without boundary, sorry, of manifold without boundary. And the idea is that you have any domain D in M. M does have a boundary. This domain has non-empty boundary inside of M. And then if you have a bounded above subsolution of the Laplace equation with the appropriate Neumann boundary conditions on D1M, then the supremum over D is attained on this part, is necessarily attained on this part of the boundary of D. And vice versa, this kind of maximum principle is actually equivalent to the parabolicity. So this is the weak formulation of the thing. And the thing is that this is very useful. Again, here I give a sketch of the proof. The proof, to some extent, is not much different from what you can do in the case of manifolds without boundary. So I will not actually spend any more time on this, also because time is running short. I should like to point out, actually, that probably the difficult thing was not so much giving a proof as realizing what was the right condition in order to have really the equivalence of the appropriate form of the Alford's maximum principle, which gives equivalence to the previously defined parabolicity. So the idea is that you have to consider all possible domains, and that the relevant part of the boundary has to be that one. Here I go. This is the proof of the other direction, but as I said, it is fairly straightforward. Okay, and another thing that should be stressed is that the functions that appear in this formulation are not required to satisfy any kind of condition on this boundary, and this is encoding a Neumann condition. And another significant thing is that in the case where we actually consider, instead of a domain, the entire manifold, then we have this version of the Alford's maximum principle that is also useful in the application. And in this case, we have absolutely no boundary conditions, because this is, in this particular case, it really says something about that the boundary is entirely negligible, which is essentially the meaning of parabolicity. Parabolicity means that the boundary at infinity is negligible. In this situation, you have the same thing. The boundary at infinity of M is completely negligible, and this holds using test functions which are completely supported in the interior of M. So there is no boundary condition on dm here. Okay, and as I stated at the beginning, using parabolicity, we can obtain this version of the height estimate. We have a complete Riemannian manifold. We assume, as in the compact case, that the Ricci curvature is non-positive. And we further assume that the volume of balls in N grows at most quadratically in the radius. Then you take a domain with a smooth boundary, and you have a graph over the domain M with the boundary on the slice at height 0. Constant curvature h greater than 0 with respect to the downward pointing Gauss map, and this is a requirement that we need to impose in the general case. If sigma is actually bounded, so if U is bounded, then sigma is contained in this slab. And the proof, as we will see, is actually very similar to what we have seen in the compact case, but it depends in a crucial way on the possibility of extending the volume estimate from the base manifold to the graph. It is straightforward that if you have a graph and you have a control on the gradient, then you can control the volume of balls in the graph by the volume of balls in the base manifold. A control of the gradient of the graph function is actually something fairly difficult to achieve, and Professor Rosenberg in many of his papers has to work quite a bit to obtain that from geometric data. And here the point is that it is possible to obtain this control of the volume of balls in the graph by volume of suitable balls in the base manifold, assuming that the graph function is bounded and that the mean curvature is bounded. This is a much nicer geometric condition which applies, for instance, in the situation at hand. So in any case, this is the result. It follows adapting ideas by Peter Lee and Wang, and with this result, we can go through the proof of the. Sure. This one? Right. Well, the conclusion here is actually that there is only a volume estimate. So for now, yes, because the idea, roughly speaking, is that you want to control this thing. Right? And so by usual considerations, intrinsic balls are contained in extrinsic balls. So if you control this, you're done. And the Lee and Wang trick is to write this in this manner. This term is bounded by 1, and so no problem. And this term is actually related to the vector field whose divergence gives the mean curvature. So you cook up a suitable vector field whose divergence makes, actually the vector field is this one. So if you consider rho is a suitable function, which is something like this. If you apply the divergence theorem to this vector field, you will have this term plus others, and the others are either expressed in terms of this vector field computed against the normal, or its divergence, which is actually the mean curvature. So this is how it goes. And as I was saying, once you have that, N has quadratic volume growth. So by the lemma, sigma has quadratic volume growth. So by the theorem, sigma is parabolic. And I pull back the metric from sigma to m, and m sigma is parabolic. And then the proof is exactly as before. Using, instead of the maximum principle for compact manifolds, you use parabolicity, and specifically you use the Alfors maximum principle. So this is the proof. And I mentioned before that there is this condition on the graph. The graph has to be bounded. I need to know this to begin with. But in important cases, actually that condition can be dispensed with, because if m is 2, 3, or 4, and the sectional curvature of n is non-negative, then by results by Chen and Albert, Neller, and Rosenberg, we do know that the graph is necessarily bounded, and we obtain as a corollary this complete extension of the height estimate in exactly the same kind of assumptions that were considered before, without the extra assumption on the boundedness of the graph. Another aspect of parabolicity which is relevant to this talk is related to global divergence theorems. Essentially, if you have a manifold without boundary, the integral of the divergence of a vector field is 0. In the case of a manifold with boundary, the integral, compact manifold, this is the situation, the integral of the divergence gives the integral of the boundary data, and E is the exterior unit normal. Okay, as in the case of manifolds with boundary, you have versions of this divergence theorem which holds on parabolic manifolds, provided we assume suitable integrability conditions on X and on its divergence. And the version that holds and that it's relevant here is this L2 divergence theorem. So you have a manifold which is parabolic with non-empty boundary, and a manifold with non-empty boundary. Then it is parabolic if every vector field which satisfies these conditions for every vector field, this particular version of the usual version of the divergence theorem holds. Again, something like this essentially says that the boundary at infinity of the manifold is negligible. I only need to integrate X along the boundary of M. And the proof is essentially, as in the boundaryless case, based on the fact that parabolic manifolds have families of suitable functions which approximate the unit function in the W1 to local norm. And another thing that I'm going to use is a Liouville type theorem for the mean curvature operator under volume growth conditions. So this is exactly the same volume growth condition that we discussed before. The notions of parabolicity can be extended to other operators, for instance, the P Laplacian instead of the Laplacian, giving rise to P parabolicity, or more general to these divergence type kind of operators. And it is not difficult to give a proof of this result, which essentially says, again, that if you have a subsolution of the mean curvature operator which satisfies suitable boundary conditions on boundary of M, and it's bounded, then U is necessarily constant. These are two further volume conditions that imply the result. Should be noticed that this is actually has to be interpreted in the usual weak sense. And using this, we have the analog of the slice theorem for graphs that we started with. It is exactly the same as the one with we saw at the beginning in the case of compact manifolds, with some additional assumptions. So first of all, we have here that the volume grows of M grows at most quadratically. You have the graph with non-positive mean coverage with respect to the downward pointing Gauss map. You assume, this is a technical condition, essentially that the graph is bounded above on the boundary. This amounts to saying that condition, and then you have one of these two assumptions: either the graph on the boundary lies on this slice, or the Gauss map at the boundary makes a suitable angle with the interior normal of the slice. If, moreover, the graph, the part of the graph that is contained in a half space has finite volume projection on the downward slice, so this means that the thing cannot be always very big. At a certain point, it may not, if I cut the graph, the part of the graph that stays above a certain level may not be necessarily compact, but it has finite volume. This condition is actually required to get parabolicity. And under these conditions, you conclude that sigma is a slice of the product. And a brief comment on the proof. The main point is to show that the graph is bounded above. The rest is an application of the, essentially, either the alpha maximum principle or the Liouville type property for the mean curvature operator on parabolic manifolds. And this is, so the main point is that to show that U is necessarily bounded above, and this goes sort of a common argument. I know that this function, the divergence is non-positive for the assumptions on the graph MC, on the part of the graph above a certain level. C is chosen in such a way, MC is entirely contained in the interior of M, and MC has finite volume, so it is actually parabolic, and it's typical. You have something which is subharmonic, sub-something on a parabolic thing, and you conclude that it is actually harmonic. So this is harmonic, and then knowing that it is harmonic, you use the Liouville type theorem for the mean curvature operator on the graphs to conclude that it is a slice. So this is the result. A few words in the minutes that I have on parabolicity and minimal graphs. So as I said at the very beginning, we are considering essentially a notion of parabolicity based on Neumann boundary condition on the boundary of the manifold. There is another, so this is actually has a probabilistic interpretation, and has to do with the reflected Brownian motion. In the case of manifolds without boundary, actually one has a version of, one can characterize parabolicity in terms of subharmonic functions which satisfy Dirichlet boundary condition. So typically you would say that a manifold is parabolic if whenever you take a compact domain in a function which is subharmonic and satisfies, say for instance, zero boundary conditions on the boundary, in the outside domain, then the function is constant and equal to 0. This is, for instance, the definition used by one of the characterizations used by Peter Lee. Yeah, it has to be bounded, of course. Bounded and zero boundary conditions, then it is 0, certainly. The two notions, parabolicity and this one, are equivalent, and it is essentially based on the fact that you are considering bounded domains. In the case of manifold with non-compact boundary, you could still assume as a definition of parabolicity requiring Dirichlet boundary condition on the boundary. And you get a very fruitful definition, which is very well adapted to the kind of, for instance, slice results that we've been seeing, because typically there you have functions which vanish on the boundary. And being able to say that the function is constant and equal to 0 actually means that you do have a slice. So what are the connections between, so here I was actually mentioned that some names connected to this application of parabolicity. And again, this definition of parabolicity, it is given here. I call it deparabolicity for Dirichlet, and it said what I said. You have a function is bounded above harmonic and with the Dirichlet boundary condition, then U is a constant function. The absorbing Brownian motion is recurrent in probabilistic terms. And what are the relationship between the two? Again, here the Alford maximum principle comes in, because using the Alford maximum principle, you show that if M is parabolic and U satisfies this, in the weak sense, this differential inequality, then the supremum of U on M is equal to the supremum of U on boundary of M. So applying this proposition twice to U and to negative U, you obtain that if it is parabolic in the sense of Neumann boundary condition, then it is D-parabolic. So in fact, deparabolicity is a weaker notion, and from this point of view, it should hold under more general conditions. The thing is that, as we've seen, besides parabolicity, we've seen that volume growth conditions are relevant in the study of, for instance, constant mean curvature submanifolds and or graphs. And apparently there is no immediate relation between deparabolicity and quadratic area growth. However, since I know that quadratic area growth implies Neumann parabolicity and Neumann parabolicity implies deparabolicity, we have a pretty quick proof that a manifold which has quadratic area growth, it is in fact D-parabolic. And so all results that have been obtained exploiting D-parabolicity actually follow from volume growth conditions. And again, since the volume of intrinsic balls is dominated by that of extrinsic balls, we also see that properly immersed surfaces in Euclidean space with quadratic area growth are D-parabolic. And I'm done. Mix conjecture that any complete properly embedded minimal graph over a proper subdomain of the plane is D-parabolic. Neal gave a probabilistic proof of this result, and this result follows from what we have seen, area growth, Neumann parabolicity to Dirichlet parabolicity, using this last result by Li and Wang on the extrinsic volume growth property of of graphs. So, for instance, a complete minimal graph in Euclidean 3 space is necessarily parabolic, and hence also deep parabolic. This is all. Thank you very much.